Let's say we have the repeating decimal 0.4008, where the digits 4008 keep on repeating. So if we were to write it out, it would look something like this: 0.400840084008, and keeps on going forever. What I want you to do right now is pause the video and think about whether you can represent this repeating decimal as an infinite sum, as an infinite series, and then think about whether that infinite series is a geometric series. So I'm assuming you've given a go at it, so let's think about it. So for each term of my infinite series, I'm going to represent one of these repeating patterns of 4008. So for example, I will make this 4008 my first term. So this could be viewed as 0, and this 4008 represents 0.4008. Then I could make this 4008 my next term, or my next term will represent this 4008. And that means it's 0, and this 4008 is the same thing as 0.0000408. And then this next 4008, well, that represents 0. And we have 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8. 4008. 4008. And then we would just keep on going like that forever. So we're just going to keep on going like that forever. So hopefully there's a pattern here. We're essentially throwing 4 zeros before the decimal every time. And we could just keep on going like that forever. So this is an infinite sum. It's an infinite series. The next question is this a geometric series? Well, in order for it to be a geometric series, to go from one term to the next, you must be multiplying by the same value, by the same common ratio. So what are we multiplying when we go from 0.4008 to this one right over here, where we add 4 zeros before the 4008? What are we multiplying? Well, we move the decimal 4 spots to the left, so we're multiplying by 10 to the negative fourth, or you could view it as we're multiplying by 0.001. Sorry, one more zero, 0.01. 10 to the negative 1, 2, 3, 4. To go from here to here, well, same thing. Move the decimal 4 places to the left. So once again, we're multiplying by 0.0001. And so it looks pretty clear that we have a common ratio of 10 to the negative fourth power. So we can rewrite all of this business as 0.4008 times our common ratio for this first term times our common ratio of 10 to the negative fourth to the 0th power. So that gives us that right over there. Plus 0.4008 times 10 to the negative fourth to the first power, and that gives us that value right over there, plus 0.4008 times 10 to the negative fourth to the second power, and we keep on going. And so in this form, it looks a little bit clearer like a geometric series, an infinite geometric series. And if we wanted to write that out with sigma notation, we could write this as the sum from k equals 0 to infinity. To infinity of, well, what's our first term going to be? It's going to be 0.4008 times our common ratio, which we could write out as either 10 to the negative fourth or 0.0001. I'll just write it as 10 to the negative fourth. 10 to the negative fourth to the kth power. To the kth power. So the next interesting question, this is clearly can be represented as a geometric series, is, well, what is this sum? You might say, oh, that's just going to be 4008 repeating over and over. But I want to express it as a fraction. And so I want you to pause this video, use what you already know about finding the sum of an infinite geometric series to try to express this thing right over here as a fraction. So I'm assuming you've had a go at it, so let's think about it. We've already derived in previous videos that the sum of an infinite geometric series, and let me do this in a neutral color. If I have a series like this, k equals 0 to infinity of a r to the k power, that this sum is going to be equal to a over 1 minus r. We've derived this actually in several other videos. So in this case, this is going to be, well, our a here is 0.4008. And it's going to be that over 1 minus our common ratio. Minus, and I'll write it like this, 0.0001. 1/10,000th. So what's this going to be? Well, this is going to be the same thing as 0.4008. If you take 1 minus 1/10,000th, or you could use this 10,000 10,000ths minus 1/10,000th, you're going to have 9,999 over, or 9,999 10,000ths. 10,000ths. Once again, you could view, let me write this out just so this doesn't look confusing. 1 is the same thing as 10,000 over 10,000. And you're subtracting 1 over 10,000. And so you're going to get 9,999 over 10,000. And so this is going to be the same thing. This is going to be the same thing as 0.4008 times 10,000. So times 10,000 over 9,999. Well, what's this top number times 10,000? Well, that's just going to give us 4,008 over 9,999. 9,999. And we've just expressed that repeating decimal as a fraction. So we have succeeded. And you might say, well, maybe we can simplify this thing. And so let's see. If this is already a fraction, so we've already kind of achieved it. But if we want to get a little bit simpler, see, if we add the digits up here, 4 plus 8 is 12. So, and 1 plus 2 is 3. So this up here is divisible by 3. And this down here is clearly divisible by 3. So let's divide both of them by 3. So 3 goes into 4,008. Let's see, it goes into 4 one time. Subtract, you get a 10. 3 times 3 is 9. Subtract, you get another 10. Goes into 3 times. 3 times 3 is 9. Subtract, bring down an 8. 3 goes into 18 exactly 6 times. So our numerator is 1,336. This is no longer divisible by 3. The sum of the digits is not divisible by 3. It's not a multiple of 3. And if you divide this bottom number by 3, you get 3,333. And I think we have simplified it. I think we have simplified it about as well as we can. Although I might, well, we could check more. Let me know if I didn't. But either way, we have now written this. This was pretty neat. We saw that a repeating decimal can be represented not just as an infinite series, but as an infinite geometric series. And then we were able to use the formula that we derived for the sum of an infinite geometric series to actually express it as a fraction.